First question is describe a radioisotope. Give some properties of radioisotopes. So, what is a radioisotope? So, before radioisotope, what is isotope? The isotope means any atomic nucleus having same number of atomic number but atomic mass is different. So, atomic nucleus having same number of protons means atomic number but atomic mass is different, and those having radioactive properties is called radioisotope. Okay, for example cobalt. So cobalt having atomic number of protons 27, whereas atomic mass is 60 and 58. It is used both in case of diagnostic and therapeutic purposes, that means radioisotopes. For example diagnostic, so thyroid, renal function, lung perfusion and ventilation, and bone scanning, then PET CT and PET imaging. Therapeutic, treatment of the cancer using isotopes, for example cobalt 60. Then what are the properties of radioisotope? So if you want to buy anything which should be cheap, easily available, less cost, free from toxicity, that are the common criteria. So let's see. As it is a radioisotope, so it is harmful, so it should be easily available, which is made by usually cyclotrons. So it should be easily available, it should be of low cost, that is less expensive, should be free from any toxicity, should emit a small amount of radiation which is not harmful to the patient. Emitted radiation from radioisotope should have the ability to penetrate to the body so that it can be detected by suitable method. So whenever we pass the radiation, that is radioisotope, it should be detected, otherwise it will be purposeless, so it will be not beneficial for us, and should have ability to follow the normal physiological process of the body, because whenever we put something in the body it should be excreted, so it should follow the physiological process of the body. In some cases we have to tag, so should have the ability to tag with various materials for applied to the body by appearance by appropriate radiopharmaceuticals. And likewise 18FDG, which is there is 18FDG, that is fluorine, there is glucose, so which is tagged actually, and should have suitable half-life, that means not too short, not too long, that hamper not too short that hamper imaging, and not too much long that unnecessarily increase the patient dose. And purity of radioactivity, purity, because it's if it is not pure material we can't use, the purity of radioactivity should be maintained for low dose to the patient to prevent degradation of the image. If it is not pure, there will be formation of blur image, or the required image will not form, and so it will degrade the image quality. What are the roles of radioisotopes in diagnostic radiology? So roles of radioisotope in case of diagnostic radiology, same thing, that is renal, brain, liver, thyroid, that is 99 technetium. So there are 7 we are commonly used: 99 technetium, iodine 131, gallium 67, indium 111, thallium 201, fluorine 18 and 51 chromium. So 99 technetium, so it is used for kidney, brain, liver and thyroid. Iodine, that is thyroid and kidney. Gallium, that is for tumor imaging, that is localization of the inflammatory Oh no, no, sorry, sorry. Yes, gallium 67, that is for tumor imaging, and indium 111, that is infectious process, that is abscess formation. So abscess wall is usually defined by indium. 201 thallium for myocardial perfusion imaging, heart. Fluorine 18 for lung imaging and PET scan, and 51 chromium RBC leveling for RBC volume. And these are the diagnostic radiology. What are the therapeutic uses of radioisotopes? So therapeutic uses are there are following six compounds, not atomic nucleus we can use, that is cobalt 60, selenium 90, phosphorus 32, aurum 198, caesium 137, and iodine 131. So let's see the what are the uses of that. Cobalt 60, gamma decay for brachytherapy in carcinoma of cervix. 99 selenium, that is beta decay contact therapy for pterygium, that is pterygium formation usually occurs in the medial canthus. So this one is pterygium, and which is given where contact therapy is given for the treatment. Phosphorus for bone carcinoma, malignant tumor, and treatment of polycythemia vera. Then aurum 198, that is malignant ascites, pleural effusion, and pericardial effusion. So these are basically whatever the effusion we use aurum, aura. 137 calcium, treatment of the carcinoma of cervix. So cobalt and calcium used for carcinoma of cervix. And iodine, treatment of hyperthyroidism and carcinoma of the thyroid and metastasis. So there is we have make a summary, and we can see that renal scan is done by two things: 99 metastable technetium and iodine 131. Thyroid by same thing. Liver 99 technetium. Brain 99 technetium. Heart is by thallium, and RBC, that is 51 chromium 51. So these are the summaries in overall. What is the basic principle of the TLD batch? That is thermoluminescence dosimeter. So this one is a figure which is described, and before this figure I will like to go to the next page. So we can see in above is the conduction band, and in lower side is the valence band, and here is pure crystal, here is impure crystal. So in pure crystal you can see the electrons or atoms are placed in uniform manner. So there is no external or any extra electron can be placed or trapped. So atoms are present at regular intervals, so no space between the conduction band and valence band, no space. Whereas here these are scatteredly placed, so some intermediate regions between the valence band and conduction band, and trapping of electron is occurs. So here you can say scattering, and here is some intermediate regions that is often not filled by electrons, so here trapping of electron can occurs, that is impure. So incident photons is come, and this one is valence and this one is conduction band, CF2, and when it is emitted by any means, the electron goes from valence band to the conduction band, and there is the impurities between their intermediate region and which is trapped here. So it is trapped, and this one is trapped in the same way until we put heat. So at one time we put heat here, so this one is put it here, and we put heat. On heating there is visible light, so by the amount of light we can calculate the dose. By and the electron was gone from the ground state to the higher state, or lower energy state to the higher energy state. So by releasing light it again comes back to the ground state, and the light is measured by multiplying the PMT tube. So by measuring the PMT tube we can calibrate the amount of radiation dose. uh, Before now let's move to the previous. Now we can see ionizing radiation means that is the photon. Here is conduction band, and this one is the valence band as usual. So by any means ionizing radiation goes, and there is impurity, so it is trapped here by the electron trapping, and on this one is trapped, and on heating it is come to the ground state by releasing the visible light, and visible light is measured, so we can calculate the dose. So what is TLD? So TLD is basically what is a personnel monitoring device with a special chemical compound, that is lithium fluoride, that retain deposit energy from the radiation exposure. So it is a device, that is monitoring device. Personnel means it is used for employees, usually those who are work in certain place, that is personnel, with a special chemical compound. So in electron tapping there is one special chemical compound, that is called lithium fluoride, that retain the deposit energy from the radiation exposure. What is the principle or mechanism of the TLD batch? So the mechanism is TLD, that is thermoluminescence, is the emission of thermo means heat. So by putting heat we can emit the light, that is thermoluminescence is the emission of light from a crystal on heating after removal of excitation, that is ionizing radiation. So by this way we have put it, and electron is trapped, so when it removes light is released, that is the thermoluminescence, the emission of light from the crystal on heating after removal of ionizing radiation or excitation. A radiation dose cause the electrons in the crystal to move from the low energy state to higher energy state. So they are talking about this one. So from the lower to higher energy state, by radiation dose causes the electrons in the crystal, this one is a crystal, so move from the low energy state to the high energy state. Impurities in the crystal, so here is the impurities as I have shown in the previous picture. Here is the impurities, so it is trapped. Impurities in the crystal creates energy trap, providing metastable state for electrons. So it is a metastable state because once it is it releases light on heating, it comes to the stable state, that is ground state. Some of these excited electrons are trapped in the metastable state, and these photons can be collected with PMT tube, means photomultiplier tubes. Means if it is in 5, then we can increase in number and we can measure the amount. So it is directly proportional to the number of number according to the multiplication. So it is does not destroy or error the value. That is the PMT tube, and by proper calibration the dose delivered to the crystal can be measured. So it talks about the first for thermoluminescence. Then radiation dose causes the electrons in the crystal to move from low energy to high energy state. Impurity crystal creates energy trap, providing metastable for the electrons. Some of these excited electrons are trapped in metastable state, and these photons can be collected in the PMT tube. By proper calibration, the dose delivered to the crystal can be measured. Now, so a diagram of film batch, how film batch identify the types of radiation. So first the film batch diagram and how film batch identify the types of radiation. So TLD can measure but it cannot differentiate the types, whereas film batch can differentiate the types. So there is something specific about this. So basically we have drawn the color is not basically that much important, although I have put on the red, then you can put, and this one is the particular, means the person's details, because it can be used by only one person, so that we can record the amount of radiation the person has exposed during period of time. And there are some layers. So this one is the photographic film in light proof cover, and this then aluminum layer, then lead layer. So at last lead, then aluminum, then photographic film cover in the light proof cover area, that is plastic. So we can measure beta gamma radiations. So this one is the film batch dosimeter. And how can we identify so there are layer. If it goes up to the open window, then alpha, beta and gamma radiation. Then it cross the plastic layer, then beta and gamma. Aluminum, then beta, that is high energy, and gamma. And if lead filter, then X-ray and high energy beta radiation. The batch so how can I identify the film batch? So the batch incorporates a series of filters. A batch incorporates a series of filters to determine the quality or type of the radiation. Film batch are composed of chemically coated film, that is mostly a silver bromide AgBr emulsion covered by a light tight paper in compact plastic container. So there will be reaction. Halide, that is bromium with light proton, Br plus electron, and Ag, that is silver plus electron, that is Ag, silver. Radiation causes the blackening of the film material. So how much radiation is exposed depend on the optical density represents the radiation dose. The degree of blackening of the film known as optical density represents the radiation dose. What is the difference between film batch and TLD? So film batch and TLD. Film batch low cost record can be kept and dose and type of radiation can be measured both. Then TLD high cost cannot keep into the record and only dose can be measured. As I have mentioned that TLD can measure only the dose, not the type. And what about the reuse? So film batch cannot reuse like a photo studio. Once we use and print, it cannot be reused. In the same way TLD in the same way but on similar that TLD can be reused. Level of detection: film batch cannot detect very low, whereas TLD it cannot detect different types, but very low level radiation can be measured. Chemical compound that is used, recently we have studied that AgBr, and here is lithium fluoride as in the thermal emissions process. This one is a laborious process, film batch. This one is less laborious process. Here we measure the that is the film, so density, and the TLD batch is emission of light, so light. What are the advantages of the film batch? So low cost, record can be kept and can measure both dose and type. What are the advantages of TLD? So very low level of radiation can be measured, reusable and less laborious process. So both have some advantage and disadvantage. These are the differences: the cost, record, and dose and type. These three advantages, and that is totally here. Whereas low level of radiation, then reusing and less laborious process. These three are the here advantage, which is the opposite of that. Then lithium fluoride is used here, AgBr is used here, and density is here, and light is here. Give the basic principle of the gas filled radiation detectors. Name some type of detector with example. So gas filled detector, the most widely used radiation detector, a device that respond to ionizing radiation by producing electrical pulses. So graph of the dependent of the voltage pulse height and DC charge. So this one is a DC charge, and this one is the voltage pulse height. A, B, C, D, E. We have divided the 5 regions. So each one having a name, and we proceed according to that. So this one is up to So region A, B, C, D, E. So region A, that is DC is very much relatively low. So this one is up to here, then here, then here, then here. So DC is very much relatively low. So recombination of positive ions and electrons occur. So as a result, not all ion pairs are collected and voltage pulse height is relatively low, as you can see up to here only. So if the DC voltage increases, it does increase as the DC voltage increases. So if DC voltage increases, the pulse height will increase, and so increase in pulse height, recombination decreases. Reason B, here DC voltage is as you can see here, reason B. So DC voltage is sufficiently high. So negligible recombination occurs, and this region is where the type of detector called ionization chamber operates. So this one is called ionization chamber operates. Then this region is the C. So DC voltage is sufficiently high, up to this level is sufficiently high in this region. So electrons approaching the central wire. So here during this wire, while it works, there is central wire, and approaching the central wire attains sufficient energy between the collision as between the electrons and positive ions. With the electrons of the gas atoms produce new ion pairs. So no number of electrons increase. So as there is collision with the electron and produces new ion pairs, so increase number of electrons. So electric charge passing through the resistor may be up to 1000 times. So in case of region C, 1000 times greater than the charge produced initial by the radiation interaction. And this region where the type of detector is called proportional counter. So B is the ionization chamber, this one is the proportional counter. Proportional means with directly proportional means according to the um, number, means if increase by 5, then there also increase by 15 if directly proportional, like that. Region D is DC voltage. So here is so high, here is sufficiently high, here is also sufficiently high, there is low, and here is so high that even a minimally ionizing particle will produce very large voltage pulse. The initial ionization produced by the radiation triggers a controlled avalanche of electrons which head towards and spread along the central wire. This region is called the GM region, that is Gregor counter works range of the voltage. And region E, this one is the region E. So high enough, so high, sufficiently high, low, this one high enough for the gas to completely break down. So there is ionization, even minimal ionization. Here is so much high ionization, that is up to 1000 times, and here completely break down and thus useless to detect the radiation. The next question was, what are the types of detectors with examples? So there are three types basically: gas field detectors, scintillation detectors, and other detectors. So gas field is that group A then B, then C. No, sorry. Group A, there is no detection. That is region A, no detection. In region A, no detection as there is only recombination. In region B, that is ionization chamber. Region C, that is proportional chamber. Region D, that is GM tube, Geiger-Müller region or chamber or tubes. Scintillator detectors are two types, solid and liquid. Others are semiconductor detector, film, that is film batch, and TLD, that is thermoluminescent detectors. Write for note down scintillation detector. So before we starting, we will look first at the figure. So this one is the basically scintillator, and this one is the photomultiplier tube. So first we look at the scintillator. So there is incident of high energy photons. So there is sodium iodide, and there are some compounds which is used for different type of detection. So here is a recoiling electron, and these are the scintillator photons. So these comes here, and there is photocathode. This one is called photocathode. Here is photocathode. So photocathode transfer the or convert the scintillation photon into electron. That is photocathode. That is the function, and we can see this one, that is the electron, and these are the diodes. So diodes. So basically diodes do multiplication inside that. So here 1, then here will be 2, then here will be 2 to the 4, then 4 to the 16, like that. It's multiplication, and finally it will produce as current falls here, and here is the charge, that is suppose this one is 200, 400, 600, 800, 1000, 1200, like that volt. And this one is the connected with each other by voltmeter, positive HV, and here is also positive HV. So this one is scintillator, photomultiplier tube, photocathode, HV, diodes, anode. This one is cathode, negative charge, and photoelectrons we can see. This one is photoelectrons, incident high energy photons, recoiling electrons, scintillator photons. So what is the mechanism? A scintillator is a material that converts. Scintillator is a material that converts energy lost by ionizing radiation into light. So scintillator is a material that converts energy, the energy lost by ionizing radiation into light. Finally, that is light. Ionizing radiation interact with scintillator, which produce a pulse of light. So when it interacts, it produces a pulse of light. An incident proton or particle ionize the medium. So an incident photon or whatever the particles ionize the medium. That is this one is the medium. And ionized electrodes slow down, causing excitation. So once the ionized electrons slow down, it will cause ionization, because again it returns to the ground state, and excited states immediately emit light, and that is emitted protons strike on light sensitive surface, and the light interacts, that is photoelectric interaction with the photocathode, which results in the production of the electron. So this one is the electron. The electron is multiplied in and this electron is multiplied in the PMT tube, photomultiplier tube. So this one is the photomultiplier tube, and that has a series of focus diodes. So this one is diodes. These are the diodes, photodiodes with increasing voltage. I have already said 200, 400, 600, 800, 1000 like that. So with increasing voltage results in an electrical signal. So there is electrical signal. The number of counts dependent on the activity that is present. So basically it depends on the activity, how much it is present. The energy of the electron and consequently the associated current is proportional to the incident energy of the ionizing radiation. So whatever it comes here, that is actually proportional to the this. So in case of scintillator, there is in scintillator medium. This one is PMT tube, and this one is scintillator. So in scintillator we use the following things: sodium iodide, which is thallium activated, TH activated, we can see most of the time thallium activated. It detects gamma rays. Zinc sulfide, ZnS, it alpha. Then cadmium iodide, which is also here, proton and alpha. Then organic anthracene and stilbene, anthracene and stilbene, that is beta radiation. So next, write short note on density and attenuation. So what is radiographic density? So what is simply density? So amount of darkening of certain area on an X-ray film is called density of that film, that X-ray film. Exposure of radiation on X-ray film produces film blackening or density. So whenever something is exposed, so not X-ray, whenever we expose to the normal light, even the X-ray film produce some opacity or blackening, that is called density. That is negligible, but that is also density. So density is log 10. What is the incident divided by the transmitted? So suppose this one is the film, and this one is the incident, and the how much it is traversed. So how much it is blackened, that is the film density. So its formula is density equals to log 10 divided by initial radiation divided by transmitted light intensity in case of film. It depends on the amount of radiation reaching a particular area of the film and resulting mass of metallic silver deposited per unit during development. What are the factors? So factors are kilo voltage potential, milliampere second, time, so and film focal distance, and thickness and nature of the part being radiographed. So kilo voltage per milliampere second, time, FFD, and thickness and nature of the part being radiographed. And you can see this one is light penetration, how much it occurs, and this one is optical density. So more the density, there is less light penetration. So in case of 0, 100, 0.5, 50, 1, 10, 2, 1%, 3, 0.1%. So it is inversely proportional. So increase in density decreases light penetration. I have already showed you the figure, that is incident intensity of the light, and this one is traversed intensity of light. This was a film. So how much it is like that is refractive density. Then what is attenuation? So attenuation means attenuation of photon beam. So it talk about the photon beam. So this one is the basically suppose a photon beam, and this one is the radiation, that is number of photons, and this one is the traversed number of photons n. So it is combination of scattering and absorption. So this one is beam, light is passed or the incident photon is passed, some passes direct, some got traversed in this way, some in this way, some absorbed here. So according to definition, attenuation means absorbed plus some scattered, but those who have traversed is not included in the attenuation. So this one is the detector, that is basically X-ray film, and this was in the human body. So formula is n equals to n naught e to the power, that the base of logarithm mu x. So n is the number of incident photons, n naught, n is the number of transmitted photons, e is the base of natural logarithm 2.718, mu is the linear attenuation coefficient, and that means the amount of thickness traversed, and X-ray is the observer, x is the observer thickness, how much thickness of the observer is. It is of two types, LAC and MAC, linear attenuation coefficient and mass attenuation coefficient. LAC is a measure of the fractional attenuation per unit length, means how much length of the material traversed. A MAC is the provides measure of the fractional attenuation per unit mass of material encountered. So here is length of material traversed, a mass of material encountered. MAC is basically LAC divided by density is called MAC. So what are the factors influencing attenuation? So energy, high energy equals to more penetration and less attenuation, and less energy equals to less penetration and more attenuation. So inversely proportional with the energy, attenuation is inversely proportional with the energy. And other things are matter, so density, atomic number, electrons per gram of the human body tissue or whatever the tissue we exposed. So density, atomic number, electron per gram increases attenuation. So more the atomic number, so more will be, there will be photoelectric interaction, and more will be attenuation. Atomic number, so electrons per gram is also the same things. So density, atomic number, electrons per gram, and there is energy.